Okay. Before we continue to next topic, okay, at the end I would like to ask one very important question is that since it looks like the kernel, okay, the pattern of the kernel looks very critical when we analyze those data, okay. No matter it is image, so I will have a 2D kernel, and each kernel describe pattern on the image. We're trying to find image, those patterns. No matter it's a dot, no matter it's a curve, it's a straight line, something like that. But the one important thing is that how do we decide the pattern of a kernel? Okay, sometimes you may forget how those weights are obtained from our neural network. So let's go back to the very first neural network we're talking about. Okay, so it's right here. We have an input value, we have a y, we have n data, right? We have n data. Those n data will help us to find the minimum value of the loss function, and then we'll do partial differentiation to tweak, to change, to modify our weight, so that all our training data, n training data, and their corresponding y target will have the lowest those value. Okay, they will tweak those weights to make this happen. So right here it's almost the same. Okay, it's almost the same. We have input data, which is the image. Okay, for each image it has 784 features. They are all real number. Okay, to indicate it is a black or it is a white pixel. Okay, at the end we have y. We have the actual value of, we have the actual target. Okay, this image, okay, it's 4 or 5 or 3. Okay, we have all those labels to help us to identify it is which digital number, which digit it is. Okay, so all of the weights used in this neural network, including the weights of convolution, so which is the pattern of the kernel, the weight in the dense layer, the weight used by all of the layers, they are trained. We don't know how they come up with the value, but basically by partial differentiation. Okay, we have input x, we have output y, and we set a goal. Okay, it is a classification problem, so the loss function should be cross entropy, right? So the cross entropy value of this neural network by using the n inputs. Okay, basically I think in this data set we have more than, I think, 60,000 images. Okay, and all of them are labeled images. Okay, and they are handwrite digits. Okay, we have more than 6,000 images. Okay, those images will help us to find all those W's, those weights, to minimize the cross entropy value at the end. Okay, so basically we don't have to set what is the pattern of the kernel looks like. Those patterns are automatically learned by using these 60,000 images and its corresponding y by using cross entropy. Okay, so we don't know. So basically we don't set this weight. We simply just randomly select some random values at the first place, and the partial differentiation will help us to find the lowest value, which is by using what we introduced last week. Okay, by using different optimizer to help us to find the lowest cross entropy value. of this neural network by using the 60,000 images, right? Okay, so you don't have to bother yourself to set all those kernel. You only need to set how many kernels you want, what is the size of this kernel, you want padding or not, and how many layers, how many different pairs of convolution and pooling you like to use, and at the end there are several dense layers, right? How many dense layers you like to append after the convolution network, okay? And what is the size of this neural network? For example, it is 3136, and next layer is 128, next is 10. Okay, with 1 to 10, you have to decide how many neurons, 1 to 28, or 200, or 300 you like to use. So those parameters you have to decide by yourself. Okay, so that is. So basically, you can find a lot of different implementations by using CNN and MNIST or other images dataset. So basically, you simply just Google CNN and MNIST or CNN image classifier. Okay, you can find all those informations, all those examples. Okay, you simply just download one. So for example, if this image classification is provided by officially by TensorFlow. So here, okay, run in Google Colab. You can simply just click it and copy the code from Google's example, and we can just take a look at here. I think it's right here. We have introduced this before. Okay, here is the model. It's quite simple. After you design your model, you can write code like this. Okay, it's still a sequential model because we stack different layers. Okay, first layer is the preprocessing layer because the image has to be preprocessed. Okay, so you can take a look at the explanation at the top of this page. Okay, so next one is CO layers, CONV2D. That means convolution layer, and it's 2D. 16 means I would like to have 16 kernels. 3 means I would like to create kernels which size is 3 by 3. Padding means yes, and also I append an activation function after this convolution layer, which is ReLU function. And next one, max pooling 2D, which means I would like to do max pooling. Okay, it has no parameters because it has default parameters. Okay, and then another 2D convolution layer. Okay, have 32 kernels, 3 by 3, do padding and append a activation function after it, and do convolution again, and do pooling again, next pooling again, do convolution again. Use 64 kernels to describe a pattern. 3 by 3, padding, ReLU, and then max pooling 2D at the end. Okay, the flatten is a commonly used function, which means I collect all the information from the previous layer. Okay, for example, right here, as right here, right? Because at the end of this the second pooling, we have 64 pieces of data, and each of them is 7 by 7. So in total, I have 3,136 data can receive, right? So I simply just collect all of them in a single vector. So that means flatten. Okay. So the symbol right here, and it creates a dense layer, which is 128 neurons, and at last it is a dense function. Okay, which is number of classes is 5. Okay, this example, the number of classes is 5. Okay, and you simply just run it by using a compiler. Okay, the optimizer is added, which we talked about before, and the loss function is categorical cross entropy. Okay, and we would like to know the accuracy result, so so on and so forth. And usually, sometimes when you use TensorFlow, okay, there's a very useful function called summary, model.summary, which means it will output a visualized result of your model. So you can see that, okay, after the first layer is called rescheduling, the second layer convolution 2, third layer max pooling, convolution, so on and so forth, so on and so forth. And we have at this last a flattened layer to collect all the information to a single vector and dense. So we can see that at the second column, which is output shape, which means what is the current size of your data. Okay, so every time when you do pooling, okay, if you do the padding, okay, so let's take a look at this one. Okay, say convolution 2D, right? So the size is 100 by 180 by 180 because you're padding it, so the size is still the same. The second one is pooling, right? It's 90 by 90. That means we have a 2 by 2 pooling kernel, so that the size shrink from 180 by 180 to 90 to 90, because we have the 2 by 2 straight 2 pooling kernel. And then we do another convolution, right? Since we're padding, so the size is still 90 by 90, but we have 32 kernels right now, so we have 32 pieces of data. Each one is 90 by 90, and we do pooling again. It's a 2 by 2 pooling, so it shrink again the size from 90 to 90 by 90 to 45 by 45, and the pieces is the same, 32 pieces. And we do convolution again. The size is the same, right? Because we do padding, and the kernel size changes to 64 because we say we need 64 kernels. And we do pooling again from 45 by 45 to 22 to 22. And we do flatten. We collect all the information from the previous layer. Okay, so 22 times 22 times 64, theoretically it should be 30976. And we do dense, so we shrink the data and shrink the data again to the 5 classes. So it is a very useful function, which is summary. It will describe what is the shape and name, and the most important of all, and the third column is parameter number, which is number of parameters, which means how many different weights that you use. How many weights? Okay. For example, in the convolution, in the first convolution, we use 448 different weights. So we will use the x and y and our loss function, which is categorical cross entropy, to train this 448 weights to a proper value, and this value will make our cross entropy to be as low as possible. Okay, so that is the parameter used by this layer. So so on and so forth, so on and so forth. And as you can see that there will be tons of weights that need to be trained. So basically you can see that the total parameters right here in this very simple three layers of convolution plus pooling plus 2 dense layer. In total, there are nearly 4 million weights to be trained. And as we mentioned before, at the first place, they are all random values. And we do partial differentiation to make them to approach to some other values to make the loss function, loss value to be low. Okay, so that is. Okay, so basically you can use a fit function to do such kind of training. Okay, to train all those 4 million weights. Okay, so that is you will take some time to train this weights. Okay, because every time you feed FEED. Okay, you feed some data to your network, to your neural network. Okay, the feed function will help you to do the partial differential calculation to find where is the next direction for each weight. So we'll go one step more toward to the next weights prime. Okay, until several different iteration right here. Okay, so we have 10 epoch. Okay, so it takes times. Okay, let's take this for example. Okay, each step, okay, it takes some seconds. Okay, so the lost value, right? Because at the first place, those weights are randomly assigned, right? So right here, we train those weights toward to some weight prime. Okay, so we can see that the loss value right here at the very first round, the loss value is 0.8064, right? So we gradually feed more data, which is images, okay, for in this example, to the neural network, to the feed function. The partial differentiation will give us new weights, and these new weights will make the loss value, which is cross entropy in this example, we're getting lower. For example, 0.5, 0.3, 0.2, 0.1, 0.1, 0.06. If you have more data, the loss will become even smaller. Okay, so if you do so, your accuracy, of course, will become higher and higher. Okay, so let's go back to our very first slide right here. Okay, as I mentioned before, in neural network, most of the time, we will partition our data into 3 different data sets. One is for training, so we use the training data right here to help us to find the lowest weight, to tune our weight. Okay, so the second data set right here is validation data right here, right? So it is an independent data. The third one is testing data. So let's see how they are used. So right here we can see that we have 2 additional value right here. It's called VAL loss, which is validation loss and validation accuracy. Training data is used to help us to modify weights and get lower loss value and get higher accuracy, right? But at this moment, because we tune our weights by using those training data, we'd like to know, what if I have another data set, which is called validation data set? What is the loss value of the validation data set? And what is the accuracy by using this validation data set? So we use the second data set to calculate all those loss value. Okay? So here's the loss value, and here is the accuracy of this loss value. I have to say that because we train all those weights by using training data, so at the end, those weights are quite fit those training data. 好，中文再讲一遍哦。因为我们是用 training data 来修正那些 W， 使得那些 W 可以让我们有比较低的 loss。好，在这个例子里面是 cross entropy 的。所以你 train 了很多轮之后呢，这个 neural network 会渐渐的会有点，我们讲的白话一点，就是走火入魔了啊，就是它会只根据它现在看到的这些 training data 修改它的 weight。好，那我们会有另外一个 data set 叫 validation， 对，它是一个独立的 data set 切出来的哈。这些 data set 是没有拿去做 training 的，它是在 training 的每一轮的过程中顺便测一下。如果我是拿 validation data set 的话，那拿来试 现在这些 weight 的话，那它们的 loss 是多少？很明显可以看到，这个好像不太对吧？它的 loss 怎么会越来越高啊？对吧？0.9、0.9、1.2、1.2、1.2、1.4、1.6，这什么意思啊？这个通常它的意思哦，这个其实是个烂例子啊。这个意思是说，这个 training 的整个过程当中啊，好像我们拿 training dataset 过来修正那些位，已经有点走火入魔了。有点走火入魔，意思是说，它已经失去了这个一般性。它在这个 training dataset 里面可以得到很好的效果，可是你随便拿一个真实世界里面的另外一个 dataset 来测试的时候，你会发现，哎，这个 loss 好像看起来怎么越来越高啦，然后右边的 accuracy 怎么也好像都没有像 training data 那样看6×9嘛，7×9嘛，9×8嘛，到最后，可是右边怎么看起来都是6×3左右？就是说你在辨识这个 image 的时候，分类的时候，怎么成功率都只有6×3？好，所以实际上你可以看这些的值来判定这个 neural network 是不是学的太走火入魔了，它失去了所谓的一般性，失去。那我们为什么会？可是这个状况怎么会发生呢？是这样子哈，我们在收集资料的时候啊，一般来说应该就是普世的，比如说我们发一些问卷去收集你的身高体重啊，收集你的什么之类的，去网上收集资料啊，收集访物的资料啊，收集图片的资料，对不对？好。这些资料应该都有一些 distribution， 对不对？所以我们在 training data 的时候，应该是从这 distribution 里面去做抽样，抽出一个某个集合。那这个集合，你看 normal distribution 去抽样，抽一个比较少的样出来，应该还是 normal distribution 吧，对不对？然后你拿 normal distribution 去做一个 neural network 出来，然后会得到一组答案嘛，对不对？然后你拿一个 validation 资料，这个 validation suppose 应该也是 normal distribution， 对不对？然后呢，你拿去做 testing 的时候，你看你学的是一个 normal distribution， 然后你测的时候 validate 的时候是一个 normal distribution， 应该会非常完美才对。理论上是这样子。好，就是说，你有，比如我们讲身高体重这件事情好了，那你就去收集台北市里面身高体重，对不对？那按理来说，你只要你做的收集资料收集的够完整，你应该是从什么0岁的小孩到100岁的老人，他们的身高体重，然后中间的年轻人，然后还要配合那个人数，你要做的一个很完美的调查才对。在这个很完美的调查里面，你做一个随机的抽样做来做 training， 你也是一个很完美的抽样才对。可是现实生活里面基本上你很少，不太会发生这样的状况。你可能做调查的时候就很偏颇，对不对？你做台湾的这个身高体重调查啊，你都抽台北市里面的，你都不抽南投、抽花莲偏乡里面的小孩，说不定他们有些人长得特别高壮，对不对？啊，有些人长得特别瘦弱，好啊，你只抽台北市人，说不定大家都肥肥胖胖的，就不太好嘛。所以调查就已经是一件问题了。那再来是抽样，我们做出的答案呢，1到 N 个人啊，我们不是分3个部分嘛，对不对 ？training 一个部分 ，validation 然后 testing 一个部分。你有没有很认真的按照统计学老师教你的方式去抽样，做出 testing 呢？做出 training 呢？然后 training 去 train 这个 model 嘛 ？training train 出来的 model 是它就会很符合这个样子，什么样子？就是 normal distribution 的样子，对不对？那万一你抽样的时候乱抽，你又抽到那种身高比较高的、体重比较胖的，那你做出来的 train， 你用这些资料做出来的 model， 它就只适合描述身高高体重重的人的模型嘛，我们现在讲模型嘛。那比较瘦小的人，你这个模型就不会合嘛，对不对？所以你等一下做 validation 的时候，你又乱抽，你抽出来的人是比较瘦弱的，然后你要做 validation， 然后你现在用高胖的人去做出来的模型，就不适合拿来预估矮瘦弱的人嘛，对吧？你的自然你的 loss 就会高，你的 accuracy 就会差，对不对？所以 training data、testing data、validation data 应该都要非常的跟母体长得很像，讲母体哈，让母体很像，这样子你 train 的时候，你虽然是 training data， 可是因为 training data 跟母体很像，所以你实际上 train 的就是母体，可以吗？母体的 model。好，那你 validation 是不是也是从母体抽出来的另外一个资料集？那你拿这个 validation 来测你的 model， 好像也是母体对母体嘛，对不对？那 validation 就会很好。那也就是说 testing 的时候，你 testing 的抽样是不是也从母体抽出来的？然后你也抽得很好，那你的 testing 的 distribution 也会很靠近你的母体，对不对？所以你用 training 做的 model 在 validation test 级上，在 testing 级上，这三个不同的级上，就会因为都很靠近母体，所以就会很相似，所以你做出来效果就会好。可是老实说，我们拿到的资料啊，比如说你这个手写的资料，他们之前有跟你讲说，他给你的 training data、test data 有很抽样很完美吗？有调查的很完美吗？有全世界所有人的手写的样子吗？那你抽样的时候是从全世界的母体里面抽出跟母体很像的人做 training、validation、testing 吗？都没有。所以我们在真实世界里面常遇到的状况就是，资料集不完美，资料集没有表示母体，资料集很偏颇，然后 validation 呢也很偏颇 ，testing 也很偏颇，所以他们之间是没有凑不起来的。然后你的 accuracy 跟 loss 值就会不够低 ，accuracy 就会很差。好，这是中文联的参考意见了哈。Okay, so every time when you do model training, okay, my suggestion is you partition your original data into 3 different data sets. Okay, you train your weights by using your training data. Okay, every time, every epoch, every time you modify your weight, okay, you validate your model by using validation data. Okay, so we have 2 lines right here. The blue line, okay, is the training accuracy and the training loss. Okay, the orange line is the validation loss and the validation accuracy. We can see that the accuracy of validation dataset is not quite good. Only 63 or 5% of data can be classified into correct class. Okay, and the loss will gradually increase. So basically, your model is very fit your training data. However, it's overfit, so that the model cannot correctly predict another dataset, which is validation dataset. So basically, there are some problems of your dataset. For example, if you the zero training data set and validation data set, they are similar. Okay, maybe yes, maybe not. Or if you train your model too many times to fit your original training data, so that is this model is specifically served for the training data, and for the validation data is not quite fit, so the prediction is not that good. Okay, so here is the result. So sometimes we have the problem of overfitting. Okay, we'll talk about this topic later. Okay, so that is data. Okay, there are some example and data set right here, so you can click the things, take a look at this code, try to read them and realize how to write code by using convolution neural networks. Okay, so we have covered convolution and pooling. Okay, it has 2D versions, you have 1D versions, and you can take a look at this API. Those API will describe how you what kind of parameters should be used. Okay, you should set those parameters in these layers. Okay. So before we so we have 10 minutes. Okay, 10 minutes is not enough for us to start next topic, which is length and space. So I think we can stop right here, and we'll talk about length and space next week. Okay, since next week is still length and space. Okay, we'll talk about next week. So we stop right here. Make sure you scan the QR code. You take a look at those example. Okay, MNIST, CNN, image classification. Yeah, basically those things I have already covered all those concepts in this 3 hours class. Okay, so make sure you know how to implement. Okay, you can just download code from this different example. Try to run them. Try to figure out how convolution actually works. Okay, so we'll go over landscapes next week, and we have homework this week. So basically, I will announce the homework this afternoon. So we'll take some time. So take some time, okay, to write your homework. Okay, make sure you understand what is convolution neural network. Okay, so I think we can stop right here, and see you next week. Okay.